Welcome back to the second to last week of new material. This is Physics 235, week 13, day 1, scheduled for release on Monday, April 13th. And today we're going to talk about image formation, like we did last time, but this time from refraction and from lenses. This is going to cover sections from the book out of Volume 3, Chapter 2, Sections 3 and 4. So first, let's start off with just regular old refraction, in a situation a lot of you have probably found yourself in before. Looking at something underneath the surface of water or looking at fish through a fish tank. So here we have a fish tank filled on the inside with water and on the outside by air, and we have a fish in there. And we want to try to figure out where our brain thinks this fish is, or where the image of the fish is. So let's first consider if we were standing off on this side of the tank. To actually observe the fish, we would need rays that travel from the fish to enter our eye. But in order to locate the image, we can draw any rays we actually want to, as long as they're going in the general direction of our observation point. So we wouldn't want to draw rays that go out this way because we're looking at this fish tank from the left-hand side. So we at least want to draw rays that pass through the left surface of this fish tank right here. So let's draw a couple of those rays. The rays might come into the surface like this and then be bent outward due to Snell's law. And then a second ray to do the same thing. So I've exaggerated this a little bit, but now these two blue rays, after they've been bent after passing into air, are going to tell us where the image of the fish is. Because remember, your eyes are dumb, so your eyes assume these light rays have always been traveling the same direction. So we trace our light rays back from whence they came and find out that they cross at this location right here. So this is where our brain thinks the light from the fish came from. So we will see the image of the fish right here if we look from this side of the tank. We can also look from other sides of the tank and see something similar. If we look in from the top of the tank, we can draw our light rays again coming from the fish, bending outward away from the normal because of Snell's law, and then we can trace our rays back to determine the location of the image of the fish. Let me do this one more time on the far side of the tank if our view were out over here. Same process, we draw any light rays we can that pass through that surface of the fish tank, and then we can trace those light rays back to determine where it seems like they came from, and that will be where the image of the fish seems to be located. So the black fish is the actual original fish, the object, and the other three, the blue, the red, and the green, are the images of the fish that we would see if we look from various sides of the tank. So you can see that these three observers, blue, red, and green, don't agree on where the fish is. But in all cases, the fish appears closer to the surface, closer to the edge of the tank than it otherwise would. And an interesting phenomena here is if we put our viewer over here looking from the corner of the fish tank, well, this viewer can see both this red ray right here and this green ray right here. So this viewer will actually see two of the fish, one through the top side of the tank and one through the right side of the tank. And I usually like to explore this idea about image formation from refraction from Snell's law by talking about spearfishing. So I'm going to go through that same process here. So let's clear a little bit of room and draw ourselves what a spearfishing setup might look like. We will have the surface of the water, and here's some land over here so that we can actually have our person standing on land. And we have our spearfisher person right here. And they are trying to catch this fish that is underneath the water by throwing a spear at it. So this is the actual object. This is where the fish actually is. And I want to draw at least 1 or 2 rays to figure out where the image of the fish is. Now you might notice that the light ray actually travels from the fish to the fisher person's eye, but I drew the light ray starting from the eye and headed down towards the fish, and this is okay because the path of light is always reversible. Or the path of light rays is always reversible. So right here is the image of our fish. So the question I have from you is, if you want to hit this fish with a spear, where should you aim? Should you aim directly at where the fish appears, above that, or below that? Remember, you can't see the actual fish. All you see is the image of the fish. So based on where the fish appears to be, the image of the fish, think about where you should aim. And it will turn out that the correct answer here is that you actually have to aim deeper than the fish appears to be. And there's actually a helpful picture from your textbook that can illustrate this process. I've placed this image in the upper right-hand corner of the screen, and you can see that the actual rod is shown here in dark orange. And the actual rod, or the actual spear, is completely straight. It's a rigid object. It's not going to bend just because it's gone underneath the water. But the rod will appear as though it's bent. For every point on the rod that is below the surface, the same effect will happen as did with the fish over here. All of the rod that is underneath the water will appear closer to the surface than it is, so it looks to our eyes as though the rod is bent, even though the rod is actually traveling in a straight line path. So if you were to aim the rod at the image of the fish, say this little bit I'm drawing in brown is the rod would actually go straight into the water and hit the image of the fish. So the actual rod would go this way and hit the image of the fish, but that's not the same thing as hitting the actual fish. So for the portion of the rod that's underneath the water, the image of that portion of the rod would appear to bend at the surface. So for this spear to actually make contact with the fish, you need the actual spear to hit the actual fish. And for that to be true, you need the image of the spear to hit the image of the fish. So you actually have to aim lower than the fish appears to be. On the other hand, there's a corollary question to this. What if you have a laser pointer? Should you aim that laser pointer directly at the image of the fish, or directly or someplace above or below that point? This is a very different question, because the spear will not actually bend, but will appear to have bent because of refraction, but the spear is a physical object. The laser pointer, on the other hand, shoots light, and light does actually bend when it hits the surface, even if it doesn't really appear to. So the short answer here is, to hit a fish with a laser pointer, you aim directly at the image. So let me draw this in blue on my diagram. The image of the fish is here, so if you aim laser light directly down at the fish, well, the light's not going to continue in a straight line path because it's light. It refracts at surfaces, and the light will bend. And due to the reversibility of the path of light, we know that light that we're shining in with the laser going this direction will bend the exact same amount as the light that came up here from the fish to our eyeballs. So the second half of Chapter 2, Section 3 does a pretty good job of explaining how refraction works in lenses, but I'm not going to go over that in detail in this video. Mostly we'll be working with the thin lens equation. So now I want to talk about thin lenses, and we're going to go through a lot of the same process here we did with spherical mirrors. There are two main kinds of lenses. There are converging lenses and there are diverging lenses. That's based on what the lens does to various light that's coming into it. When light comes into a converging lens, after it passes through the lens, the path of that light will be brought closer together. And diverging lenses, on the other hand, will spread light further apart. And there are different kinds of converging and diverging lenses that you can see in this image that I've attached here. The first one here in the first row is called biconvex because we have a convex surface on both sides of this lens. The middle one is called plano-convex because one side is a plane, thus the plano, and the other side is convex. The last one is called meniscus convex because both sides curve the same direction. We actually have a convex side and a concave side, but this is still a converging lens, and you can tell because it's thicker in the middle than it is at the edges. And then for diverging lenses, the same thing will be true. We'll have mainly three different kinds: biconcave, with concave surfaces on both sides; plano-concave, with a straight face or a flat face on one side and a concave surface on the other; and meniscus concave, where we have one concave surface and one convex surface, but the concave surface here has a more aggressive curve to it, a smaller radius of a curve to it. So the easiest way to tell if a lens is diverging or converging is whether it's thicker in the middle or at the edges, and diverging lenses will be the thinnest in the middle. Many of the similar features that we found with mirrors will also apply to lenses, with the major difference that light will pass through a lens where light bounced off of a mirror. So we will still be able to define a focal point in the same way we did before. For a converging lens, when the light comes in parallel, it will all be brought together and cross at a point called the focal point. And the distance between the lens and the focal point is still called the focal length. Just a brief note here. When light passes through the lens, I've drawn it as though it only bends when it passes through the center line of this lens, and that's fine for your ray diagrams, but I want you all to know that the light actually does bend separately at both surfaces. So when this ray comes in here at the bottom, it would first bend at one surface and follow a straight line path within the lens, and then it would bend at the other surface as well. But for the purposes of our ray diagrams, we can just draw things as though they only bend along this center line of the lens here, the line perpendicular to the optical axis. Then for diverging lenses, something similar to before happens. And again, I'm just going to pretend that the light only bends when it reaches this center line here. So the light will come into the lens as normal, and we're drawing this with parallel light coming in because it's easiest to demonstrate what the focal point is with parallel light rays. And this time, the light rays will spread out because that's what a diverging lens does. It spreads the light out from however close together it was before. Then we can follow the your eyes are dumb approach to trace each of these outgoing light rays back and see where they cross. And all of the light rays appear like they came from this point here. So this will again be the focal point, but it will be a virtual focal point. And the distance between the focal point and the lens will still be the focal length, and it will turn out that this is going to be a negative focal length, just like before. And the focal length for the converging lens will be a positive focal length. And you may be wondering where the spherical aspect comes in here, because mirrors we talked about were all spherical mirrors. And in a sense, the lenses we're going to talk about are also spherical lenses in the following way. So here we have two circles that overlap a little bit. And the first one has a radius that we're going to call R1, and the second one has a radius that we are going to call R2. And the actual lens here is in the intersection of these two, as though it's at the center of the Venn diagram. So it's this area here that I'm shading in blue is the actual lens. And these two radii, R1 and R2, are going to help define the focal length of this lens based on something called the lensmaker's equation. The lensmaker's equation states that 1 over the focal length of this lens is equal to the index of refraction of the lens divided by the index of refraction of the surrounding material, usually air, minus 1. That whole thing times quantity 1 over R1 plus 1 over R2. And I just want to clarify a couple of the n values here. The lens itself, that is your n2 value, and the surrounding material is n1. So usually we have our lenses in air, so n1 is just going to be 1. Now I want to note that those values for r, the radius of curvature of those two circles of which the lens is the intersection, or rather those two spheres of which the lens is the intersection, can be positive or they can be negative. And I want to write these down. So the sign conventions for the radius says that the radius is positive if the surface is convex towards the object. So that means we need to know which side of this lens we're going to be on in order to determine whether our lensmaker's equation is going to give us a positive or a negative focal length, or in order to determine whether R1 and R2 should be positive or negative. So what we're going to do here is we're going to choose a location for the object. So let's assume for now the object is on this side, is on the left side of the lens. Well, one side of the lens is defined by this circle right here that I'm outlining in green. So this is part of the circle with radius R2, and on the side facing the object, it is convex. So this means R2 would be positive in this case. And to switch to a different color red, the other surface of this lens that I am mousing over in red is concave towards the object. So this means this radius, the one that goes with this circle, has to be negative. Except that's R1, not R2. So then we know that R1 and R2 are the appropriate positive and negative values, and then we can go through this process and figure out what the focal length of the lens is. I just realized I actually have a mistake in this formula here, because I was thinking through this as I was typing it, or writing it out on the screen, and I realized that if my equation were as I have written down here at the bottom, then I would get a positive focal length from one side and a negative focal length with the object on the other, and that shouldn't be right. It shouldn't matter what side of the lens you look from, it is either converging or diverging. So I double-checked in the textbook and determined that my mistake was right here. This is supposed to be a minus sign between the 1 over R1 and the 1 over R2, and that will allow the answer to be either converging or diverging consistently, no matter what side of the lens the object is on. So you should get the same answer either way. Now for the rest of this video, I want to go through the same thing we did last time and actually draw some ray diagrams. Work through them with the thin lens equation and work through them with our ray diagrams. But to do that, first we're going to have to update our sign conventions a little bit and then review the equations we're going to use. And our sign conventions are going to be the same as they were for mirrors for our object distance, our object height, and our image height. And indeed, for the focal length, we'll have a similar sign convention. The focal length is going to be positive when we have a converging lens, just like the focal length was positive when we had a converging mirror. And the focal length is going to be negative when we have a diverging lens, just like the focal length was negative when we had a diverging mirror. Note that which type of mirror or lens is converging or diverging will be different between mirrors and lenses. So a convex lens is a converging lens, but a convex mirror is a diverging mirror. So the definitions of concave and convex versus converging and diverging are flipped, but the part that is the same is that converging is still a positive focal length and diverging is still a negative focal length. The only other real big difference we have is for our image distance. And our image distance is defined as positive if the object, or if the image is on the opposite side of the lens as the object. And the image distance will be negative if the image is on the same side of the lens as the object. This is slightly different from mirrors, because for mirrors, the image distance was positive if the image was on the same side of the lens as the object. But this is just a function of the fact that light passes through lenses but bounces off of mirrors. So the part of this rule that is the same as compared to mirrors is that we still get a positive image distance for real images, and we still get a negative image distance for virtual images. And that is consistent with what we learned about lenses. The only other thing we really need to do here before we get to actual ray diagrams and specific examples is review our equations and talk about our principal rays. Our equations are the same as they were before. 1 over f equals 1 over di plus 1 over do. And this again is known as the thin lens equation. You may be wondering why we keep specifying that this is the thin lens equation. And that is because, like mirrors, spherical lenses do have a spherical aberration. So when we use thin lenses, lenses that aren't too thick in the center, that aren't too bulbous, either concave or convex, then the spherical aberration is small and can mostly be ignored. So that's why we keep saying thin every time we refer to these lenses. And like before, we have the equation for our magnification as the image height over the object height, or the negative image distance over the object distance. But now we're going to need some new principal rays. Things will mostly be the same as they were before, but we won't have quite as many principal rays. Our first ray will be the same rule as before. If the ray comes in parallel to the axis, it will go out through the focal point. And that ray might look something like this. If the ray comes in from the left-hand side, parallel to the optical axis, it will pass outward directly through the focal point. Then, our second ray is just the reverse of this. If the ray enters the lens through the focal point, it will exit parallel to the optical axis. So this ray might look something like this. Coming into the lens, passing through the focal point, and it will exit parallel to the optical axis. Note that these rays I'm drawing are not coming from one object. I'm just drawing example rays of what this process might look like. And last but not least, any ray that passes through the center of the lens will not bend. So if we have a ray coming in here from the left that is going to pass directly through the center of the lens, then that ray will continue on without bending at all. And these are the three principal rays we're going to use in the 4 examples we're going to do in order to locate our image. Now the first situation we're going to do is a lens with a focal length of positive 10 centimeters. So we know this is a converging lens or a convex lens. And we're going to choose an object distance that is 25 centimeters, or about 2.5, precisely 2.5 times the focal length. So that would be out here somewhere. So let's draw each of our 3 rays. The red ray, the ray that comes in parallel to the optical axis, we draw all of our rays from the tip of the object arrow, and we draw the ray coming in parallel to the optical axis, and that ray will pass out directly through the focal point. Our blue ray, again, comes from the tip of the arrow and passes through the focal length on its way to the mirror, and then exits parallel to the principal axis. One thing to note is that this blue ray is always going to determine the height of our image. No matter where these rays cross, if I had only drawn the blue ray, no matter where the rays end up crossing, my image will still end up being the same height, and that's going to be a negative image height. So pay careful attention to this blue ray, as it will tell you a lot about the magnification of your image. And we already know where our rays cross. We could already draw the image, but let's draw our last ray here just to make sure we understand. Again, the ray will come from the tip of the object and will pass directly through the center of the lens without bending. So our green ray will look something like this. All of our light rays cross, and the location where they cross is the location where the image appears. Since we drew all of our rays from the tip of the object arrow, our rays will all cross at the tip of the image arrow. Then we can draw the rest of our image. So let's see what we can predict from this. We can say, well, our image is closer to the lens than the object. But the image is also still outside the focal length. So we're expecting an image distance that is definitely larger than the focal length, that being 10 centimeters. But we're also expecting an image distance that is smaller than our object distance of 25 centimeters. Our image is real because the rays actually cross. Additionally, our image is on the opposite side of the lens as the object, so we expect a positive image distance. And our image is inverted compared to the object, so we expect a negative magnification. And last but not least, the image is smaller than the object, or the image is reduced. So we expect a magnification whose magnitude is less than 1. So let's grind through the calculations and make this happen. First, we have our thin lens equation, 1 over f equals 1 over do plus 1 over di. So plugging in, we have 1 over 25 centimeters. Sorry, that's not right. We have 1 over 10 centimeters for our focal length equals 1 over 25 centimeters for our object distance, plus 1 over di, and we can solve for di and obtain the value of 16.7 centimeters. So our image distance is positive and in the range we expect. Then we can calculate our magnification. If we had object and image heights, we could use them, but in lieu of those, we'll have to do negative di over do, which gives us negative of positive 16.7 centimeters divided by our object distance of 25 centimeters. So we get a magnification of negative 2/3, which is both negative and has a magnitude of less than 1. So let's do another example. Shush, Lillian. So this time, let's look at a situation where the image is placed precisely on the focal point of a converging lens. We can still draw our rays here. The ray comes in parallel to the principal axis, will travel outward through the focal point. Our second ray, the ray that comes through the focal point, will pass outward through the focal length. Well, a ray passing through our focal point and the tip of the arrow is vertical, and never hits the lens. So this ray, we can't really use this ray. We don't know how it refracts because it never actually hits the lens. So we're not going to use that one. And last but not least, we have the ray that passes through the center of the lens unbent. And we can see here that our outgoing rays are parallel, and this means that no image will ever form. So let's back this up with some math. Taking 1 over f equals 1 over do plus 1 over di. We can plug in our 10 centimeters, positive 10 centimeters for f, and our 10 centimeters for the object distance, plus 1 over di. And this means that you find that 1 over di is equal to 0, which means that di equals infinity. So the image will only form an infinite distance from the lens, which means the same thing we found from our ray diagram. The outgoing rays are parallel, so there will be no image that forms here, so we can't even calculate a magnification because there's no image. For our last example with a converging lens, let's put the object inside of the focal point, a distance of 4 centimeters from the lens which still has a positive 10 centimeter focal length, and let's draw our rays. The red ray is easy. The ray comes in parallel to the optical axis and passes out through our focal point. The blue ray, like with spherical mirrors, we can't draw a ray from our object through the focal length because that won't ever hit the mirror. So we reverse the path of this light and imagine a ray that came in through the focal length before it hit the object and continued traveling along that path. This ray is going to miss the mirror. So in real life, this ray would not be refracted, but for the purposes of our ray diagrams, if you remember that center line of the lens that I keep talking about, then you can just have the ray bend whenever it reaches that line, even if it misses the mirror. This will still help you locate the image accurately. So this ray comes in through the focal point and will come out parallel to the optical axis. Remember, it's this blue ray that sets our magnification, so wherever our image happens to form, we expect it to be upright and enlarged, which means this is going to be a virtual image. Last but not least, we have the green ray, which passes directly through the center of the lens and is not bent whatsoever. So, these rays do not intersect, so we know we do not have a real image. And you might be confused, saying, Brendan, this is a converging lens. It's supposed to bring the light together. And it is, to an extent. A converging lens will bring the light more together than it currently is. So over here on the left side of the lens, the light is spreading out rather rapidly. And after passing through the lens, the light is not spreading out as much. So you can look at this or see this by comparing the green ray to the blue ray. The green ray travels in a straight line, so it's a really good reference point here. Before the light hits the lens, the blue ray is traveling up and to the right, but then is bent to its right slightly to travel parallel to the principal axis. So this blue ray is not diverging as much from the green ray as it was before. So the light has been brought closer together than it would have been without the lens there. So, to find the image, we employ the tried and true your eyes are dumb method. So we take the path of each of our light rays and trace them back. And we find that our rays actually cross, or at least seem to have crossed at this point right here. So this is where we draw the tip of our arrow for our image. And this is a virtual image because the rays do not actually cross, they just appear to an observer on this side that they all came from the same point. So, since we have a virtual image, we expect our image distance to be negative. The image is further away from the lens than the object, so we expect the magnitude of our image distance to be more than 4 centimeters at the very least. And our image is upright, so we expect a positive magnification. And our image is enlarged or bigger than the object, so we expect the magnitude of our magnification to be greater than 1. Working through the same math as before, we can plug in our positive 10 centimeter focal length, we can plug in our 4 centimeter object distance, and solve for our image distance to get that it is negative 6.7 centimeters. So we do have an image distance that is negative, and we do have an image distance whose magnitude is greater than 4 centimeters. When we calculate our magnification using negative di over negative do, that's negative of negative 6.7 centimeters, divided by our object distance of 4 centimeters, we get a magnification of positive 5/3, which is both greater than 0 and has a magnitude larger than 1. For our last example, we're going to take a diverging lens. So this is a lens with a focal length this time of negative 10 centimeters, and we are going to put the object exactly twice as far from the lens as the focal length. So the object distance will be 20 centimeters. And we can still draw all of our principal rays with slight difference than before. So our first ray comes in parallel to the principal axis. And I'm going to draw this part in orange or yellow because it's not actually what happens. But we might be tempted to say, well, this ray goes out through the focal point. But what I've just drawn in yellow, is what happens with a converging lens. So for a diverging lens, remember your focal points are kind of on the opposite side of the lens as you expect them to be. So our ray can't go out this way. It has to go out through this focal length on the left side of the lens. So does that mean our ray comes back this direction? Well, that's also not right, because this is not a mirror, it's a lens. The ray has to pass through the lens rather than bounce off of it. So it will turn out what happens is we do use this focal length on the left side, but we draw a dotted line that passes through the focal point and meets up inside of the lens with our incoming ray. And it's along this line that our ray exits the lens. So the ray does pass through the focal length on its way out of the lens, or it appears as though it passes through the focal length, but it's the focal point on the left side of the lens instead. Now for our blue ray. Normally, if this were a converging lens, we would pass through this focal length on our way to the mirror. Don't draw this yet. But this is what we would do for a converging lens. So now, instead of aiming for that focal point, we need to aim for this focal point over here. So our ray will travel in as though it's traveling straight towards that focal point that is on the right side of the mirror. But once it hits the lens, not the mirror, and then after passing through the lens, that light ray will then be parallel to the optical axis. We can see now that this is setting the height or the magnification of our image. We expect our image to be smaller than the object or reduced. Thankfully, with the green ray, there's not anything different between converging and diverging lenses. The green ray will pass directly through the center of our lens, unbent. And just like the previous example, none of our outgoing light rays actually cross each other. They've been spread out, even more spread out than they were before, because this is a diverging lens, but we're going to have to trace our rays back in order to find our image. So the red ray, to trace it back, well, we've already kind of drawn this line on here. So tracing the red ray back provides us with the same line we had before to verify that our outgoing ray looks like it came from this focal point. The blue ray, we take our outgoing ray, the one that's over here on the right side of the lens, and trace that back. So our blue ray gets traced back in this direction. So hold on, let me draw that a little better. And our green ray is straight. So to trace our green ray back behind the lens, that path is going to be directly on top of the path the green ray followed anyway. So we can see that our rays all appear to have come from the same point, right around here, to within the limits of my ability to draw these lines perfectly straight. So we can draw our image right here. And we can already say that we know this is going to be a virtual image because the rays themselves didn't actually cross. They just look like they all came from the same point. So, real quick, some things we expect from this image. The image is virtual. So this means we're expecting an image distance that is negative. The image is closer to the lens than the focal point, which means we expect the magnitude of our image distance to be less than the 10 centimeters that is the magnitude of the focal point. Our image is upright, which means we expect a positive value for our magnification, and our image is reduced, or smaller than our object, so we expect the absolute value of our magnification to be less than 1. Let's grind through our math and see this. Again, the thin lens equation, 1 over f equals 1 over di plus 1 over do. You note that I write the right-hand side of this equation in either order. Addition is commutative. You can do it in either order. So 1 over di plus 1 over do is equivalent to 1 over do plus 1 over di. So we take the 1 over negative 10 centimeters for our focal length equals 1 over our image distance plus 1 over our object distance of 20 centimeters. And from this, we can solve for our image distance and get a value of, turns out again, it's negative 6.7 centimeters. An image distance which is negative and has a magnitude smaller than 10 centimeters. Then when we calculate our magnification using negative di over do, that becomes negative of negative 6.7 centimeters on the top and 20 centimeters on the bottom, and we find a magnification of positive 1/3, which is both positive and has a magnitude of less than 1. And even looking at our image, you could make a good case that this image right here is about 1/3 the size of our object right over here. So this is how we use ray tracing with lenses, and this is how images are formed through refraction, either through like the edge of a fish tank or through lenses which also operate on the principle of refraction. That's everything for today. Thank you for watching and have a good day.